All right, good afternoon, everyone. I hope you're having a lovely Saturday so far. Welcome to my talk about the UIPainter. It's the user interface framework of our custom game editor. Actually, I'll do this. Boom. But first, before we dive deep into our user interface framework, I want to quickly mention another fascination of mine, and that is that I really enjoy making music. You may have even seen me play at the jam earlier today. And one of the instruments I like to play, or trying to play, is my guitar. I did have one annoyance with my guitar, though, and that is that it detuned so quickly. And having to tune my guitar every time I play it added this imaginary barrier to me actually enjoying playing it. So naturally, I went on Google, and I searched for how to stop my guitar from detuning so quickly. And one of the first pieces of advice I found was that I should replace my old strings. So I bought some strings and I tried it out. And the result is that I ended up picking my guitar way more often, which contributed to my enjoyment of actually making music using it. And I believe a very similar phenomenon happens with tools. So imagine you're an environment artist and you're painting trees on the terrain. And the trees do not end up exactly where you might expect them to be, or the tool is going to be very slow or sluggish. You're not going to be inspired to make some awesome-looking landscape. And this is especially true when you're working on a game for a long time, like the 5 years we spent making Horizon Forbidden West. Over time, whether or not the toolset is pulling its weight or not will really start to affect the final quality of the game. There's this quote I quite like, which is that people ignore design that ignores people. And this is a concept that also applies to the user interface of tools. You want it to look and to feel good, and so that people actually want to use the tools. This is something that I personally really care about. So my name is Wessel Mast, and I'm a tools programmer at Guerrilla. And when I started working at Guerrilla around 3.5 years ago, I did an internship project on, well, you guessed it, the user interface framework of our editor. And in this project, I was trying to see if it was possible to get our user interface framework to run natively on the web using WebGL. This would allow our tools to be used on different platforms or on more low-end hardware. And at the time, I thought it would be tricky to make work, especially since I was just an intern, but it was actually surprisingly easy. And this tool is called the build tool, by the way. We use it to track build failures or to undo changes. And we actually have it running in the browser here. And even though this WebGL project never ended up being more than like a proof of concept, it sparked my interest with the user interface framework. And I've been making improvements to it here and there ever since. So today, I hope to share some of my excitement about this UIPainter with you all today. But first, let's roll back the clock 10 years ago. Before any of this existed, we were working on this game called Horizon Zero Dawn. And our toolset was extensive, but also pretty fragmented. To create some very basic content, you had to jump between many different applications and copy from one application to another. And none of them talked to each other that well. This resulted in a lot of work, manually copying values from one tool to another. And that's disruptive, and it led us with frustrated users. The solution was to try and fit everything into a single application, which we now call the Decima editor. And using the editor, artists and designers would be able to start up one application containing all the tools that they need to complete their workflow. When we were designing our editor back in the day, we knew that we would also want a user interface framework. And looking at our existing tools, we saw that a lot of them had like these noodle graphs with wires and with nodes, and we knew we wanted to support those. So keeping this in mind, we set ourselves a few constraints and to get something up and running. So first of all, we wanted it to be very pretty, which means having a user interface framework that works on both different display skills and is also nicely anti-aliased. So for graph-based visualizations, we wanted to be able to zoom in and out and still preserve a high level of detail. without any jagged edges. It also needed to be simple, meaning that it's both easy to understand and to expand upon. This is because we're going to build an entire game editor and support a lot of different workflows. And we wanted programmers outside of our relatively small tools team to try and extend the tools team to the tools as well. And this included sometimes also creating new UI elements. So we wanted our framework to be very simple. And lastly, it also needed to be fast, meaning fast enough to draw any reasonably complex piece of user interface in under 16 milliseconds. No one was going to want to switch to actually using our editor if the tools were going to be very slow and sluggish. So using these three constraints, while on a plane from Amsterdam to rainy San Francisco, our technical director, Michiel van der Leeuw, decided to start writing the very first few lines of a user interface framework. And by the time the plane landed, we had the newly born UIPainter had drawn its very first rounded rectangle on the screen. And now, 10 years later, we are ready to talk about it. And in those 10 years, we started using the UIPainter pretty much everywhere in our editor for drawing a wider range of complex UI, targeting different workflows and disciplines. This time, though, the UIPainter hasn't really changed that much, and we managed to achieve all the goals that we wanted to achieve. So how does it work? Let us start with an example. So some of you might recognize this logo. It is the DevGAMM Awards logo, and it's made using the UIPainter with a fancy little heartbeat animation for fun. Let's just isolate the controller part to see how it's built up. So the controller is built out of 5 different UI primitives, 3 rectangles, and 2 circles. And I've indicated all the different primitives here in different colors to make that a bit easier to understand. And this is what the code for that looks like. It might not be very easy to see, but that's what it is like on a high level. All the code is written in C++, as that is something that all our coders are used to. And as you can see, we have a painter class that has some functions to create what we call draw commands. So draw commands are small data structures that describe a primitive that the UIPainter can draw. It starts with a generic header, such as the type of the command, like a rectangle, a line, or a triangle, drop shadow and strength, clipping rectangle, as well as the current primitive group. And primitive groups are basically, they combine multiple primitives into one shape, so that as far as the UIPainter shader is concerned, they share the same shadow and glow effects. So in this example, you can see that without the primitive groups, the shadows are kind of weirdly overlapping there, and with primitive groups, they look nice and correct. So one place where we use primitive groups in our editor is the world map. So we have a lot of debug overlays in the world map, and this is an overlay for rivers, which is a combination of multiple different primitives. So when we hover over a river, that might be very hard to see, but it's fine. But you can see that the whole shape kind of gets like a glow effect, and that is because these are all separate primitives in the same primitive group. And to continue with our draw command, following the header is some very type-specific information about the draw command. So for instance, taking this, we call it a circle sector as an example. This would be the beginning and end angle of the circle, as well as the inner and outer radius, controlling the thickness of the circle sector. So all draw commands are collected in order into a single buffer, which we call the draw command buffer. And when the frame ends, we bind this buffer, and we make a single draw call to the entire screen. And we do this by just drawing one triangle and sizing it to overlap the screen. And then the off-screen parts will be automatically clipped by the GPU. This means that we basically only draw one primitive to render all of the UI for our editor. But you may ask yourself, if you only make one draw call, how do we render all this beautiful UI? So let's move over to the GPU to figure out what magic we're doing over there. So to explain this, let's start with a simple example like this slider. So if we look at it up close and we pull it apart, boom. You can see that it's made out of 4 different elements. So it's simple, really. It's two rounded rectangles and two circles. Yet the combination of them is unmistakably a slider. So how do we put these colored pixels on the screen? This is where we use the information contained in each draw command to calculate what we call, or what is called, signed distance fields. So signed distance fields are functions that return a distance from a point in space to a shape, to the edge of a shape or the boundary of it, using a mathematical equation. It's called a signed distance field because the value or the distance is positive if it's outside of the shape, which we visualize as red here, and it's negative when the point is inside of the shape, which we visualize as blue. And when it's on the edge, we show it as white and will be 0. Oops. So some of these functions are more complex. So let's start by looking at just the simplest one, which is the circle. So a circle signed distance field is just the distance from your pixel to the center of the circle, minus the radius that we want the circle to have. And we can then use this distance to introduce a little bit of color. And like I said, when the distance from our pixel to the shape is negative, we know that we are inside the circle. So we can just check if the distance is less than 0 and then set the pixel to be white, right? Well, this would work, but however, doing it this way leads to an aliased shape. It's those jagged edges that we didn't want. And this is because whether or not the pixel is inside or outside of the shape is now a binary 0 or 1 value. So we're only going to get either a gray or a white pixel. And this is always going to give us a hard cutoff. So we can change this by changing the formula a little bit. So we now take 1 minus the distance and clamp that value between 0 and 1. And this still gives us 1 for pixels that are completely inside the shape and 0 for pixels completely outside of the shape. But there's now basically a 1 pixel distance where we interpolate from one color to the other. And this means that pixels that are partially intersecting the shape will end up with the value somewhere between 0 and 1, which means that we only partially blend in the color. And this gives us anti-aliasing pretty much for free, which is cool. Woo. So it can be very hard to tell maybe from that distance, but you will be able to tell the difference when it's like a full UI and you're looking at it up close. And it's these types of changes that help make our user interface pretty, which was one of our goals. So if we bring this back into drawing the entire slider, we can use the same formula for blending in multiple shapes and accumulating a color for a pixel over time. So let's start by sampling just this pixel in the center. And it starts by being our simple gray background color. And then let's blend in our orange bar, using the exact same method that we were using before. So the blending happens in order that the draw commands were added to the draw command buffer. So we're going to pretend that this orange bar was the very first one that we're supposed to draw. Well, the pixel's inside the bar, so we can safely blend in some orange. Then we go over the remaining shapes, and they do not intersect with our pixels, so we do not blend in their color at all. And now that we've processed all the shapes, and our final color is orange, we can safely output it to the render target. Now, in a more traditional way of approaching UI rendering, all of these different primitives would have to read from and write to GPU frame buffer memory to perform their blending. But in our case, this is done all directly in the shader by just using the GPU registers. So this also works for semi-transparent colors, which means that we don't have to rely on the rasterizer to perform like any of the blending for our draw call. So this also aids with our goal of having a fast and a simple UIPainter. However, a colored shape is not all that makes up a UI element. It also needs to be interactive. So to show that it's an interactive component, we can add a little bit of glow. And here's some code for adding a very basic glow effect. I will not explain everything in detail right now, but basically how it works is it uses the positive distance value, and it uses that to basically blend in a little bit of orange. All right. And now that we have an interactive slider, we can use signed distance fields to also draw all sorts of other interesting UI elements, such as checkboxes or knobs or switches. However, while this gets us a long way, it's not the only type of draw command there is to make a complete user interface. We also have text and images. So to explain that, for text, we basically pack all the glyphs into a texture. And when the text command is added, we schedule all the glyphs for that text to be packed. This way, when we get to the end of the frame, we can fit everything into the texture in one go. We ensure that this is done before our draw call, so that the texture is ready when we want to sample from it in the UIPainter. The packing of these glyphs is done using the skyline bottom left algorithm for rect packing. And this tries to fit as many glyphs as possible into the glyph cache texture. And when we encounter a character that uses a different font or size, we can just repack it. And this way, if we zoom into some text, you'll see that the glyph cache texture gets populated with bigger glyphs. And if we zoom out again, it gets populated with smaller glyphs. And this basically assures that at all zoom levels, we get the nice and crisp-looking text. And for images, we kind of do something very similar. We just store all icons and other small images into a simple image cache. But bigger images, like for instance the tiles in the world map viewer, they are not packed into the atlas. Instead, these are bound as separate textures. And this is done to make sure that our image atlas remains small. So all the image textures and glyph cache textures, they get sent to the GPU as well. And the draw commands for glyphs and images are very basic. They basically just need some UVs into these textures. And then you're good to go. And technically, we now have everything. Oops, is that not playing? Everything. Oh, yeah, OK, sorry, my bad. But technically, we now have everything ready to draw a more complex user interface. However, we still have a little bit of time left in the talk. And that is for a very good reason. Because this is about as fast as how that would run if using only the tools that I showed you today. We only get 8 FPS on a high-end GPU. And while this is a nice-looking user interface framework, it does not meet all of our goals. We wanted it to take less than 16 milliseconds to draw the UI. And this is just not fast enough. We want it to look like this instead. So how do we get there? Well, let's bring back our slider example. If we look at the pixels we were evaluating, remember that we only had to blend in the orange bar and none of the other shapes. Yet we still had to calculate the distance to all the other shapes and fetching that draw command from the draw command buffer in order to be able to determine that. And this all causes a little bit of overhead. And while it's for a simple example, it's probably fine. Imagine a pretty standard UI like this settings dialog. Every pixel needs to iterate over approximately 600 different draw commands in order to determine its final color. And this is quite wasteful, as these pixels they only really care about a single draw command that they're intersecting, like for instance in our slide example. So how do we speed this up? It's that easy to see that, but there's now a grid on top of it. What if we partition our draw commands using a grid? And if we isolate one grid tile, imagine all of the pixels within that tile only have to consider draw commands that are intersecting the tile. This would give us an average of 3.6 draw commands per pixel instead of the previous 600 plus. And this is an average because not all tiles contain the same amount of draw commands. To some of you, this concept might sound familiar. It's called tile-based rendering, and it's used more commonly in other areas of graphics, namely light culling or screen space ambient occlusion, depth of field, etc. Here's an example of us, for instance, using it in Horizon Forbidden West. We use a tile-based approach for light compute calculations. And in a sense, what we're trying to do with the UIPainter is not too different from these light compute calculations shown here. So we have a lot of complex calculations going on that are only partially relevant to the render target. So we ended up using the same approach. Little water break. That's not in the text, by the way, but I did need it. All right, so how tile-based rendering works for the UIPainter is that when we add a new shape or draw command on the CPU, we basically make an approximation of our shape. And we then find all the tiles that overlap that approximation on the screen, and we associate our draw command with those tiles. Then we store all the tiles in what's called a tile buffer, and this is also sent to the GPU next to our draw command buffer. For each pixel, we only consider the draw commands that belong to the tile, that the pixel, all the draw commands that belong to the tile that the pixel is currently looking at. But how big should these tiles be? So we decided on making them 8 by 8. Making tiles smaller would basically increase the tile allocation overhead on the CPU, as there are now more tiles in the tile buffer. And making the tiles bigger would decrease the culling efficiency. There's another reason why we pick exactly 8 by 8 tiles, and that is because of the way GPUs schedule threads. So essentially, there's a collection of either 32 or 64 threads called wavefronts on AMD and warps on NVIDIA, and they all run the same shader in parallel. These threads are usually scheduled in 8 by 8 blocks, which would nicely overlap our tiles. And all pixels, basically, that means that all pixels iterate over the same draw commands, so that we have really good utilization. Now, in the future, we could also use this technique, techniques like wave intrinsics, to speed this up even more. But for now, it's been fast enough. And using this optimization, in the visual results are pretty much the same, but we only do a fraction of the work on the GPU. And as you can see in this example, the left-hand side is not using tile-based rendering, and the right-hand side is using tile-based rendering. It's much faster this way. So do note that adding tile-based rendering does add a little bit of overhead on the CPU, since we're now spending some time allocating tiles and approximating shapes. And when making those approximations of our shapes on the CPU, we of course want to get as close as we can to the shape that we want to draw. However, because the GPU is much better at crunching numbers, we end up being mostly CPU bound. So this means that for most shapes, we opt for just simply taking the bounding box of the shape and basically associating all the tiles within it with our draw command. This works well for almost all of our shapes, with the exception being lines. As when lines are diagonal, their bounding box gets quite big, but the actual amount of tiles overlapping the part that we want to draw is really small. However, diagonal lines are not that common in user interfaces, so we ended up running with this anyway for like 8 or 9 years without a problem, until we decided to do something a little bit crazy, which is that we wanted to start drawing wireframe mesh previews of every mesh on top of our mesh container nodes. And a sane thing to do here would be to use something like compute rasterization. However, it would take a little bit of work to implement that, and we were already using the UIPainter to draw the nodes that are right there. And since it's simple enough, why not just use it? The problem is that the UIPainter doesn't have any 3D primitives, so we did this by only using those 2D line commands. And as you can imagine, we're now sending like hundreds of thousands of line commands to the shader on every draw. So those lines better be efficient, right? And well, it was actually working better than we expected, but it was noticeably slow. With doing some profiling, we noticed that a lot of time was spent on tile allocation. And this is where we decided to add this heat map view, which basically shows you the density of draw commands per tile. And our meshes were a little bit sad. And when zooming into these meshes, you can see that the screen gets progressively more and more red, actually. And this is because these mesh previews contain a lot of diagonal lines. And so when you zoom in, those diagonal lines get bigger and bigger and start overlapping a larger part of the screen. This means that from a distance, the mesh containers were usable. But as soon as you start zooming in, the performance really started tanking, especially for very high detail meshes. The solution was to modify the algorithm on the CPU side, in this case, to account for this. So we now use a version of Zhao-Lin-Wu's algorithm to basically modify it for line width and being able to map to our tile space. And we now only allocate a fraction of the tiles for our line. And now when we zoom in, you'll actually see that it gets a little bit less red this time, because there's fewer overlapping lines. And that means that basically a simple optimization like this means that drawing meshes using our 2D renderer is actually fast enough to be used by all of our users at runtime. And it also shows the versatility of these primitive commands. So basically, by just using a couple of different commands, we can visualize entire meshes, which I think is pretty cool. And also, we have now ticked all of our boxes. We have a user interface that is nicely anti-aliased and is desirable for our users. It's remained relatively simple to understand and to expand upon. And it's now fast enough to draw a complex user interface. I mean, even fast enough to draw wireframe meshes for some reason. And by combining all of these draw commands, so basic text and images and text and primitives, you can make the diverse selections of complex user interface that make up our editor. And we do this by still only performing one draw call per frame and using a single fragment shader. Now, of course, we have identified a few ways to make the UIPainter even faster. One of the big things would be, for instance, moving the tile allocation to the GPU, because as of this moment, the CPU is the biggest bottleneck. However, the goal was to make it fast enough. And in reality, we've used the UIPainter for 10 years in our editor. And in that time, we've shipped both Horizon games, and Kojima Production actually used that editor to also ship a game called Death Stranding. And with 10 years behind us, I'm excited to see what the next 10 years of the UIPainter will look like, but I'm afraid we won't actually have to change that much, because we're probably not going to want to draw like 5 times as many UI elements on the screen, for example. And so I believe that the UIPainter has stood the test of time as a simple and fast piece of tech, and that has become a core feature of the Decima engine. All right, thank you very much. Enjoy the rest of the conference. So I'll take any questions.
Hey there, thank you for
Hello.
the talk. I have a question. Are you using the SDFs for like primitives in both in like 2D or 3D objects, like on the rendering side?
So yeah, in this example, since it's only for our 2D, so drawing the user interface, we only use SDFs for 2D. But there might be a couple places where we also use it for tools in like in the actual editor. Sorry, in like the world editor, for instance.
I was just interested, why do you not use 3D SDFs for like the preview of the assets, maybe?
Yeah, so that could be a way of doing that.
Right.
But yeah, we decided not to do it. We already had the lines, and it turned out to be fast enough. So that's also a bit of a balance always with this, right? Like, what can you get done as fast as possible? Basically, how can you get it on the screen as fast as possible, just to prototype it, and then see where you have to go from there. So we basically just used what we had, and then if later on we decide, oh, it's not going to work like that, then maybe we would have gone to 3D SDFs. But we haven't needed to.
Thank you very much.
Thank you.
Do we have more questions? Well, I'll have a little bit outside of the box type of a question. Working on something like this on development UI, does this come to your dreams when you try to sleep at night?
Yeah. believe it or not, there's actually people that make tools for a living and love it. So yeah, it's a good question, I think, because of course I don't get to work on the actual games that we're making directly that much, especially if you're working on UI user interface frameworks like this. But the thing that really like empowers me is that I can make a really cool button and then give it to an artist, for instance, and they're like, "Wow, that button looks really cool." It's not necessarily about the button, of course, but you know, you can extrapolate from there. So I like my target audience, which is people that make games. So yeah, that would be my answer.